Hey, what's up, Honors Algebra 2? We're going to learn a few calculator tricks so we can use them to solve exponential equations for messy, messy decimals. If you look at any standard TI-83, 4, or 5 calculator, you'll see a dedicated button for the natural log base 10, common log base 8. So if I needed you to perform some of these computations, log base 17 would be relatively simple. We would hit the log button, type 17 in for the argument, hit enter. And we get a decimal, meaning 10 to that decimal is approximately 17. Let's just check it out. 10 to the answer, 17 comes back. If we need the natural log of 87, we will find the ln button next to the 4. Natural log, there we go, 87. And we would interpret that result as raising e to the 4.4-ish power gets us back to 87. Log base 3 is relatively simple. We don't need a calculator. 3 raised to what power is 9? That'll be a 2. But what is a little more difficult would be how to get a decimal answer for log base 5 of 17. There's no good, easy to discover decimal that will get us that value. Now, if you do have a fancy newer calculator, you actually can compute log base 5 of 17. I'll show you how. Go into the math menu, arrow down to log base. Select the base, and that lets you input the base of 5 and the argument of 17, and we get about 1.76-ish. If you don't have one of these calculators, which is really just kind of a newer thing, we would need to figure out how to compute such a number without that cool TI-84. So back in the day, we had to use the change of base formula. So please copy this down. This allows you to compute any log of any base using whatever more convenient base you want. So if we don't like our current base of b, we could divide the original argument by the original base, all in terms of a new base. We just need to realize the new base x can be any real number and can't be 1. Just to give you a sense of where the change of base formula comes from, I'll show you kind of how you can believe it's true. And I'm going to take the same equation, 5 to the x equals 17, and we're going to do two separate things to it, always obeying the golden rule of math: do to the left side what you do to the right side. So in number 1, I'm going to rearrange this in my logarithmic style. I'll rewrite log base 5 of 17 equals x, and now we already know what that number is approximately equal to. If we try it another way, though, we will get something equivalent, but it looks different. So I'm just going to take a moment and remind you of the power property of logs. When we take the log of something that has an exponent, that exponent can jump down or plug on down in front of the original logarithm. So I do call this logging and plugging. So if I take the base 10 log of each side, that will give me a new statement: log of 5 to the x equals log of 17. And we know this x can plug on down. Oops. And I don't really know what log of 5 is, but I know it's just a number. Same with log of 17. So to solve the equation x times a number equals a number, we would use division. And I hope just from this short example, you can see how that change of base formula might be true by comparing log base 10 of 17 divided by log base 10 of 5 with our result on the other side. It is not a proof, but I hope it helps you believe that equation can be true. So let's just practice using that, and this will really model how the IXL skill about the change of base formula goes. If we want to rewrite log base 9 of 27 with common logs, that means base 10. I will take log of the argument divided by log of the base, all in terms of the new base, base 10, which I will not write. And if we compute that in a calculator, log, come on now, log, we do get 1.5. We can try the same with the natural log. Natural log of the original argument divided by natural log of the original base. Let me start that again. There we go. We get 1.5 again. And we could even do that with a base 3 if we chose. Log base 3 of 27 divided by log base 3 of 9. I know the top numerator is 3, the bottom value is 2, and 3 divided by 2 is 1.5. There is one little watch out warning I need to give you all. The change of base formula written right here does have logs and fractions. In this case, each part of the fraction has a log in it, so there's 2 logs here. Prior to today, you had learned the quotient property of logarithms. Log of a fraction we can rewrite as 1 log minus another log, and just kind of acknowledge, okay, this formula has 2 logs, this formula has 1 log. Let us try to not get them confused. So if I want to work on something like number 4, the natural log of 6 over 7, I would notice how familiar that is with what we've learned already. I would write that as natural log 6 minus natural log 7. But the natural log of 6 divided by the natural log of 7, well, that more resembles the change of base formula. And that works out a little differently. So just really watch yourselves. Okay, the next couple examples really will just help us solve any type of exponential problem, whether there's easy values or complicated numbers. We'll need a calculator to use. One of the IXL skills will ask you for base 10, and you should follow along with this example to help you with that. We're going to express our answer in exact form and then also give a decimal approximation. Okay, there's the bell. So let's isolate the exponential. We will need to add an 18 to both sides. And divide both sides by 3. Of course. Okay, so the exponential part is isolated. Now we will log and plug. Here's the logging part. Geez, really? Come on. Here's the plugging part. And I'm just going to use some parentheses so that I know what is in each logarithm. All right, if we want to get this x alone, I'm going to have to divide by everything that is not the x. And what I have right there is the exact form of the answer. That means just take it as far as you can take it without a calculator. And if we did require some kind of decimal approximation, I would just have to type this in very carefully. I am going to use the fraction capability in this calculator. If you don't have that, you'll have to divide carefully with parentheses. So we're going to have to log 418 divided by 3 in the log and divide that by 3 times log 17. So for a decimal approximation, I'd get 0.5808. Okay. Let's just try one more example here. And I'd like to show you how we can solve things now with the natural log. And one thing to just remember, I'll give you this little useful fact here, the natural log of e is 1. Log base e of e is 1. When you do spy an exponential equation with e as the base, it is most helpful to use a common log for your calculating. So we would need to still isolate the exponential. The e has the exponent, and then we will natural log and plug and continue solving. So if we isolate the exponential, I'll subtract 3 from both sides, and then divide both sides by 4. And that will give me that e to the x minus 2 equals 25. Natural log both sides. And the e minus 2 plugs on down in front. X minus 2 times the natural log of e equals the natural log of 25. But here's the great little time saver, the natural log of e is 1. So really we have the equation x minus 2 equals natural log of 25. To get the exact form, add 2 to both sides. And then if we do need a decimal approximation, we'll just type that in. Natural log 25, close the parentheses, plus 2. And that would give me about 5.2189-ish. Okay, one more little add-on for this video. When you are using one of those more advanced calculators, you can just use the base given in the problem. So isolate the exponential and identify answer base exponent. Rewrite in the logarithmic form, and then perform some algebra to isolate the x. So we add a 2, and next I'll divide by 5. That would be the exact form of your answer, and if then you required a decimal approximation, we could make that happen too. And that would be about 0.7791. So there's your introduction to the basics, and we'll solve more complicated ones together.